Hello everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we will be discussing about some definitions and terminology related to the module 2, that is regarding the bipolar junction transistor. Nothing but a transistor, or in short we can also call it as BJT. So first of all, what is a transistor? Define a transistor. So transistor is a three-terminal semiconductor device in which the current conduction is due to majority and minority charge carriers. So whereas in case of a p-n junction diode, the current conduction is due to either majority charge carriers or minority charge carriers. So that is under forward bias condition. In case of p-n junction diode, the current conduction is due to majority charge carriers, whereas under reverse bias condition, the current conduction across the junction is due to minority charge carriers. So that is why the p-n junction diode is a unipolar device, whereas transistor is a bipolar device. So that is why we can also call it as bipolar junction transistor, and where the current conduction takes place due to both majority and minority charge carriers. So we can define the transistor as a three-terminal semiconductor device in which the current conduction is due to majority and minority charge carriers. What is a base? Define base. So the transistor is having three terminals. What are the three terminals? The three terminals of transistors are base, emitter, and collector. Now let us see what is base, what is emitter, and what is collector. So first define base. Base is a terminal of transistor which is lightly doped and it is very thin, which makes the majority charge carriers to flow from the emitter to the collector terminal. So base is a lightly doped and the size of the base terminal is very thin, and the main functionality of base terminal is to make the charge carriers to move from emitter terminal to the collector terminal. So this is base, and the base terminal is represented or is denoted by capital B. Coming to the emitter. So how to define emitter? So emitter is a heavily doped and the size of the emitter is moderate, whereas the size of the base is very thin and the size of emitter is moderate, but it is heavily doped. Okay, so the base is lightly doped and the size is also very thin, whereas the emitter is heavily doped and the size of the emitter is moderate. Moderate in the sense what? The size of the emitter terminal is greater than the base terminal but less than the collector terminal. So that is why we are calling it as moderate. And the main functionality of the emitter is to emit the majority charge carriers. So we have two types of transistor. What are those? NPN and PNP. So in case of NPN transistor, the majority charge carriers are electrons and minority charge carriers are holes. Whereas in PNP transistor, majority charge carriers are holes and minority charge carriers are electrons. So here if you see this NPN transistor, so this is an NPN transistor, NPN. So this is the emitter terminal. We can take the three terminals out from the three semiconducting materials. So here this is base and this is collector. So we can also define a transistor as this is emitter here. So that means in NPN transistor, emitter is of N type, and in PNP transistor, emitter is of P type. So P type, emitter, this is emitter, and this is collector, and this is base. So in PNP, emitter is P type, and in NPN, the emitter is N type. So here, the main functionality of this emitter terminal is to emit the majority charge carriers. That means electrons in case of emitter NPN transistor, whereas the majority charge carriers in PNP transistor are holes. So the emitter will generate the more number of electrons in NPN transistor, whereas more number of holes in PNP transistor. So that is emitter. So emitter is heavily doped and the size of the emitter is moderate, whereas the base is lightly doped and the size is also very thin. Now coming to the collector. So the collector is moderately doped. That means the doping of collector is in between the doping of base terminal as well as the emitter terminal. That means the doping level of collector terminal is less than the emitter, whereas greater than the base terminal. Whereas the size of this collector terminal is very large and the main functionality is to collect the majority charge carriers from the emitter terminal. Okay, so that means the emitter is generating the majority charge carriers, whereas the collector is collecting the majority charge carriers. So here the main functionality is to collect the majority charge carriers emitted from the emitter terminal. So as it is collecting the majority charge carriers, more number of charge carriers are collected and hence heat is generated. In order to dissipate the heat, the collector is made more wider when compared to the emitter and base terminal. As more heat is generated, as it is collecting the majority charge carriers, so in order to dissipate that heat, the collector is made more wider when compared to the emitter and base terminal. So we can define the collector as a terminal which is moderately doped and the size of collector is very large, and the main functionality of the collector terminal is to collect the charge carriers. Now coming to the amplification factors. For a transistor, we have three types of amplification factors: alpha, beta, gamma. Define alpha. What is alpha? So alpha is a large signal current gain in common base configuration. It is defined as a ratio of collector current to the emitter current. Collector current to the emitter current. That means alpha is defined by IC by IE. So whereas this is the current amplification factor or else large signal current gain of a transistor in common base configuration. In common base configuration, base is the common terminal, emitter is the input terminal, whereas collector is the output terminal. As emitter is input terminal, IE is the input current and IC is the output current. So that means current amplification factor or else gain is defined as a ratio of output current to the input current. So what is output current of common base configuration? That is IC divided by IE. So that is why alpha is defined as a ratio of collector current to the emitter current. In general, the current amplification factor is defined as a ratio of output current to the input current. So for common base configuration, alpha is defined as a ratio of IC to the IE. So this is alpha, and the value of alpha varies from 0.95 to 0.98. 0.98. It is approximately equal to 1. Coming to beta. So beta is the large signal current gain or else current amplification factor of a transistor in common emitter configuration. So in common emitter configuration, emitter is a common terminal. So in that case, base is considered to be input terminal and collector is considered to be output terminal. As a base is input terminal, input current is IB, and the collector is output terminal, output current is IC. So and hence I can define the beta, which is the current amplification factor of transistor in common emitter configuration, as a ratio of collector current to the base current. Okay, that is defined as a ratio of output current to the input current, whereas output current in common emitter configuration is IC and input current in common emitter configuration is IB. So beta is equals to IC by IB, and this value varies from 40 to few hundreds. 40 to few hundreds, the value of beta varies from. Okay, so this is beta. Now coming to the gamma. How can we define gamma? Gamma is a current gain or else current amplification factor of transistor in common collector configuration. So in case of common collector configuration, base is the input terminal and emitter is the output terminal. So that means base current IB is the input current and emitter current IE is the output current. So Okay, so that is why we can define gamma as the ratio of IE by IE by IB. So the current gain of transistor in common collector configuration, and it is defined as a ratio of emitter current to the base current. Okay. Now, what is the name of, what is the other name for base width modulation? What is the other name for base width modulation? The other name for base width modulation is early effect. And what do you mean by early effect? Or else base width modulation. So, as we all know that in a PNP transistor, we have two junctions. One is between the base and emitter terminal, and the other one is between the base and collector terminal. So, let us consider an NPN transistor. This is NPN transistor. So, this is emitter terminal and this is the base terminal, whereas this is the collector terminal. So, here always you remember, in order to operate the transistor as an amplifier, always the emitter to base junction should be forward biased, whereas collector to base junction should be reverse biased. Okay, so this is the collector junction JC and this is the emitter junction JE. So if we reverse bias this collector to base junction, what happens? The width of the base region, the width of the depletion region near the collector junction will be more widened when compared to the emitter junction. As it is more widened and the p-type semiconducting material, that is base, is lightly doped, so always the doping concentration is inversely proportional to the width of the depletion region. As the doping concentration is very less for base, so the depletion region due to the reverse voltage applied to the collector junction will be more penetrated into the base region. So this will be more penetrated into the base region, and hence the effective width of the base region where the recombination will takes place will be reduced, and the variation of effective width of the base region with respect to the reverse voltage applied to the collector to base junction is known as base width modulation, or else it is also called as early effect. So that is, early effect is a variation in the effective width of the base in a bipolar junction transistor due to a variation in the applied reverse voltage to the collector to base junction, and it is also called as base width modulation. So this is early effect. Now coming to the punch through effect, define punch through effect. So it is defined as, with the increase in collector voltage, effective base width is reduced to 0, and the emitter to emitter barrier voltage becomes smaller than V0 minus VBE as the collector voltage reaches through the base region. Due to lowering of emitter junction and extensively large emitter current flows, therefore there is an upper limit of magnitude of the collector voltage. So what is happening here? So due to the early effect, what is happening? Still, if you further increase this, the effective width at some voltage, at some value of applied voltage to the collector to base junction, the effective width will become 0, which in turn reduces the input voltage VBE. And hence more emitter current will be flowing. So which in turn, that means due to this, more current is flowing through the device, and which is called as punch through effect. So that is the punch through effect, and this phenomena is also called as punch through, which in turn will increase the emitter current and also increase the collector current. Okay. So now coming to the active region, define active region. So as we all know that the transistor is having two junctions, emitter junction and collector junction. So the active region is one in which the base to emitter junction is forward biased and base to collector junction is reverse biased in a transistor. And the transistor should be operating in active region in order to use a transistor as an amplifier. So the major application of transistor is amplifier. To use a transistor as an amplifier, definitely the transistor should operate in active region. And this active region of operation can be achieved by forward biasing the emitter to base junction and reverse biasing the collector to base junction. Not only the amplifier, the application of transistor is amplifier, it can also be used as a switch. The transistor can also be used as a switch. And the transistor is said to be used as a non-switch when the transistor operates in saturation region, and it can be used as an off switch when it operates in cutoff region. So what is saturation region? The transistor is said to operate in saturation region when both emitter to base junction and collector to base junction are forward biased. So as we have two junctions here, let us consider this is the diode, this is a transistor, okay, which is nothing but the back-to-back connection of two PN junction diode. So let us consider this as the emitter junction and this as the collector junction. If this diode is forward biased, what happens? This can be act as a short circuit and this can also be act as a short circuit, and hence the entire transistor can be used as on switch. So that means in order to operate the transistor in the saturation region, both the junctions must be forward biased, and hence both the junction diodes are short circuited and more current can be flowing, and hence it acts as on switch. Now coming to the cutoff region. Cutoff region means no current should flow. When no current can flow here, when both the junctions are reverse biased, then what happens? This will be open circuited and this also will be open circuited. As both are open circuited, no current flows, and hence the transistor is said to be in off state or else cutoff region. So that is why in saturation region it acts as on switch, whereas in cutoff region it acts as off switch because no current flows. Whereas in this case, current flows because both the diodes are forward biased, right? The transistor operates in cutoff region when both the emitter junction and the collector junction are reverse biased. Now coming to the reverse saturation current. Define reverse saturation current. So what is reverse saturation current? In a PN junction diode, the reverse saturation current is due to the diffusive flow of minority electrons from p side to n side and minority holes from n side to p side. Hence, the reverse saturation current depends on the diffusion coefficient of electrons and holes, or else we can also define that under reverse bias condition, no majority charge carriers can cross the junction. For example, let us consider a PN junction diode. This is my PN junction diode. How to reverse bias this? A negative terminal of the battery should be connected to P-type material, whereas the positive terminal of the battery is connected to the N-type material. So now what happens? Holes are attracted by the negative terminal of the battery, and hence holes are moving from P-type material towards the negative terminal of the battery. Right? Similarly, electrons are attracted by the positive terminal of the battery, and hence the electrons are moving towards the positive terminal of the battery. So that means majority charge carriers are not moving towards the junction. Only the minority charge carriers. What are the minority charge carriers? Minority charge carriers in P-type material are electrons which are repelled by the negative terminal of the battery, and they will be trying to move across the junction. Similarly, holes which are again repelled by the positive terminal of the battery, and they will be trying to cross the junction to enter into the P-type material. So that means no majority charge carriers are moving across the junction. Only the minority charge carriers are moving across the junction. So as the minority charge carriers are crossing the junction, this leads to some current, and that current is known as reverse saturation current or leakage current. So as this current is flowing when the diode junction is reverse biased, so that is why we are calling it as reverse saturation current. So we can define the reverse saturation current as the current due to the minority charge carriers flowing across the junction when the junction is reverse biased is called as reverse saturation current. Okay, so that you have to remember is reverse saturation current is only due to the diffusion of minority charge carriers from P side to N side and N side to P side. And operating point. Define operating point. So the operating point of a device is also known as a bias point, quiescent point or Q point. is a steady state DC voltage or current at a specified terminal of active device such as transistor with no input signal is applied. So that means operating point is nothing but the DC voltage or current. Whenever you are considering the DC, all the AC signals are ignored. So that means without any application of input signal, so the operating current or the operating voltage across a device is known as operating point. So this is also called as bias point or quiescent point, and this operating point majorly decides the region of operation of a transistor. If the operating point lies in the active region, then the transistor is set to operate in active region, and if it is moving towards the cutoff region, then the transistor is set to operate in cutoff region. If it moves towards the saturation region, then it is set to operate in saturation region, right? So that is operating point. Now load line. So load line is used in a graphical analysis of nonlinear electronic circuit, representing the constraint other parts of the circuit placed on a nonlinear device like a diode or transistor. It is usually drawn on a graph of current versus voltage in the nonlinear device called the device characteristic curve. So that means, in short, we can also define a load line as a straight line drawn on the VI characteristic curve of a nonlinear device as load line. Okay. So now coming to the Z parameters. How can we define the Z parameters? Z parameters are defined as the impedance parameters with voltage as independent and current as voltage as dependent and current as independent variables. So these Z parameters are calculated for a two-port network. This is a two-port network, okay, where we have input port. Let us indicate this as port 1, and we do have output port. Let us represent this as output port, and the voltage drop across this one is V2, whereas the current flowing through the port 2 is V1, I2, and the current flowing through port 1 is I1, and the voltage drop across the port 1 is V1. So here what I'm saying, the voltages as dependent. So that means V1 is dependent on I1 comma I2. Similarly, V2 is a function of I1 comma I2, whereas the currents are independent variables. So whatever the parameters that we can calculate by considering voltage as dependent parameter and current as independent parameter. So these are also known as impedance parameters, and all these impedance parameters are having the units of ohms. Okay, so that is Z parameters, and Y parameters are defined as the admittance parameters with current as dependent and voltage as independent. So that means I can write the current I1 is equals to Y11 into V1 plus Y12 into V2. Similarly, I2 can also be written as Y21 into V1 plus Y22 into V2. So where we can write Y11 as I1 by V1. I1 by V1. Okay, and this can be calculated by taking V2 is equals to 0, and Y21 is also calculated as I2 by V1, where V2 is equals to 0. So these are nothing but defined as a ratio of current to the voltage, and the units for this Y parameters are mhos or else amperes per volt. So this is about Y parameters, and define CE configuration. So the common emitter configuration, base is the input terminal, collector is the output terminal, and the emitter is the common terminal for both the input and output. So the configuration in which the base terminal is considered as input, collector terminal is considered as output, and the emitter terminal is taken as common between the input and output is known as common emitter configuration. Common base configuration. The configuration in which the emitter is considered as input terminal, collector is considered as output terminal, collector is considered as output terminal, and the base terminal is taken as the common terminal between the input and output is known as common base configuration. Common collector. So common collector configuration is a configuration in which the base terminal is taken as input terminal and the emitter terminal is taken as the output terminal, whereas the collector is taken as the common terminal between the input and output is known as common collector configuration. Define amplifier. What is an amplifier? So amplifier is an electronic circuit or else device that can increase the voltage or current or a power of a signal. So which can increase or else which can increase the strength of a signal. The strength of a signal may be measured either as voltage or current or power. So amplifier is an electronic device or circuit that can increase the strength of a weak signal. The strength can be either a voltage or current or a power. Justify BJT as a current control device. So the BJT, which is nothing but a bipolar junction transistor, is also said to be a current control device. Why we are calling it as a current control device? So the BJT is a current control device because of its output characteristics are determined by the input current. So as the output characteristics are determined by keeping the input current as constant, we are calling it as current control device. Now, current transfer characteristics. So the the characteristic curve that shows the variation of output current in accordance with the variation of input current by keeping the output voltage as constant is known as transfer characteristic curve or else current transfer characteristics. Now, define BJT, bipolar junction transistor. So bipolar junction transistor is a solid state device in which the current flow between the two terminals, that is collector and emitter terminal, is due to or is controlled by the amount of current that flow through the third terminal, that is the base. Or else we can also define BJT, that is a bipolar junction transistor, as a transistor in which the current conduction is due to both majority as well as minority charge carriers, and hence we can also call a transistor as a bipolar junction transistor. Define NPN transistor. A bipolar transistor in which a P-type material causing the base is sandwiched between the two N-type material causing the emitter and collector terminal is known as NPN. Sandwiched means we are placing the P-type semiconducting bar in between two N-type semiconducting bars such that a transistor is formed, and the emitter and collector terminals are taken from the two N-type semiconducting bars, whereas the base terminal is taken from the middle P-type semiconducting bar. So we can define the transistor, NPN transistor, as the sandwiching of or else a transistor formed by sandwiching a P-type semiconducting bar between the two N-type semiconducting bars is known as NPN transistor. Similarly, PNP. In case of PNP, what we are doing? We are sandwiching an N-type semiconducting bar between the two P-type semiconducting bars. Or else, we can also define this PNP transistor as two crystal diodes connected back to back. Not only PNP, even NPN transistor also nothing but the back-to-back connection of two PN junction diodes. The left side of diode is known as emitter to base diode, and the right side of, so that is back-to-back connection. How can we show the back-to-back connection here? For example, if it is a PNP transistor, so P, N, P. This is P-type material, anode. This is cathode, right? This is cathode and this is anode. So these are negatively charged, nothing but N-type materials. So PNP, PNP transistor. If you want to form an NPN transistor, how to connect them? So first we need to take cathode and then two anodes are connected together. So this is cathode here. This is also cathode. Cathode means negatively charged. So this is N, and these two are the anodes. Anodes are positively charged. So I can say this as P, N, N, P, N. So that is the back-to-back. So we can also define the transistor as a back-to-back connection of two PN junction diodes. And how can we define PNP transistor? So the a semiconductor transistor formed by sandwiching an N-type semiconducting bar between the two P-type semiconducting bars is known as PNP transistor. Define voltage gain. So voltage gain of an amplifier is defined as a ratio of output voltage to the input voltage. So we can also define this AV as V0 by Vi, where V0 is output voltage and Vi is the input voltage, and gain does not have any units. So it is unitless parameter. We don't have any units here. Now coming to the thermal runaway. How can we define the thermal runaway? So the diode and transistor both are temperature dependent devices. So as the temperature increases, the reverse saturation current increases. So why this happens here? So this is happening due to the increase, the problem with increasing temperature causing the increasing collector current is that more current increases the power dissipated by the transistor, which in turn increases its temperature. This reinforcing cycle is known as thermal runaway, which may destroy the transistor. So what is happening? Due to the increase in the temperature, the reverse saturation current increases, due to which the electrons will acquire more energy, and hence the electrons will collide with the neighboring atoms, and hence more number of electron hole pairs are created, which in turn increases the current. So this process repeats, and the repeated process of generating more number of charge carriers due to the increment in the temperature, the current increases, and this may further destroy the device, and this is known as thermal runaway. Now coming to the current gain, how can we define a current gain? It is defined as a ratio of output current to the input current. So which is represented by AI. AI is equals to I naught by II, where I naught is the output current and II is the input current, and this is also unitless or else dimensionless. We don't have any dimensions to this current gain. Now coming to the input impedance, how can we define the input impedance? So the impedance Zi is nothing but it is defined as a ratio of voltage to the current. So input impedance means it is defined as a ratio of input voltage to the input current. So that is Zi can be given by Vi divided by II, where Vi is the input voltage and II is the input current, and the units for this one are ohms per ampere, or else we can also measure this one as ohms. So this is input impedance. Now output admittance. Output admittance means it is defined, admittance in general, admittance is defined as a ratio of current to the voltage. Whereas output admittance, so that means it is defined as the ratio of output current to the output voltage. So that is Y0 is equals to I0 divided by V0. Whereas the units for this one are amperes per volts, or else we can also call it as mhos. We can also call it as mhos. That is the symbol for mhos is this one. Okay. So this is output admittance. Now coming to the input characteristics. Define input characteristics. How can we define the input characteristics? The characteristic curve drawn between the input voltage and input current by making the output voltage as constant is known as input characteristic curve. So that is the characteristic curve drawn between the input voltage and the input current. So how to draw that? Take the input voltage on x-axis and input current on y-axis, and the graph drawn between these two parameters by making the input voltage as constant. Let us consider the output voltage as constant is known as the input characteristic curve. Okay, so input voltage is V0. So now define output characteristics. So the output characteristics are always drawn by open circuiting the input. Open circuiting the input. Open circuiting means what? By making input current as 0, or else by keeping the input current as constant. So the characteristic curve or else the graph drawn between the output current versus the output voltage with input current as constant is known as the output characteristic curve. Now explain the transistor as a switch. So the transistor, in a transistor, unless a current flows in the base circuit, there is no current can flow in the collector circuit. This property will allow a transistor to be used as a switch. The transistor can be used as on switch or off switch by changing the base. So here, as you all know that transistor can be used as a switch here. So if the transistor is set to operate in saturation, then it is said to be acting as an on switch. If the transistor is set to operate in cutoff region, then it is said to be operating as off switch. So that is how we can see that the transistor can be used as a switch. Define HI. What is HI? These are the hybrid parameters. HI is nothing but the input impedance. Okay, so input impedance, which can be defined as a ratio of input voltage to the input current. So HI is equals to VI divided by, or else let us consider V1 and V2 or V1 and I1 are the input parameters. Okay, V1 and V2 are the input parameters. V1 and I1 are the input parameters. V2 and I2 are the output parameters. So here I can define the input impedance HI as a ratio of input voltage to the input current, that is V1 divided by I1, by making V2 as 0. So it is defined as the short circuit input impedance. Means what? By short circuiting the output port, we can measure the ratio of input voltage to the input current, which is nothing but the input impedance, which is given represented by HI. Coming to the HR. HR is defined as the reverse voltage gain or else reverse voltage ratio. So here, as I told you, V1 and I1 are the input parameters and V2 and I2 are the output parameters. So reverse transfer gain or else voltage gain. Reverse means always a gain is calculated from output to the input. If you are talking about reverse voltage gain, so we should take it as the ratio of input voltage to the output voltage. So V1 by V2 by making the input input open circuited. I1 is equals to 0 by making the input open circuited. So it is defined as open circuit parameter and it is defined as a ratio of input voltage to the output voltage, which is given by HR. Now coming to the output admittance. So output admittance is also a short circuit parameter. Short circuit means it is an open circuit parameter, means we are open circuiting the input port, and admittance is nothing but output admittance is the ratio of output voltage or else output current, that is I2 divided by V2 by making I1 as 0. By making I1 as 0. That means by open circuiting the input port, we can measure the output admittance. It has a ratio of output current to the output voltage, and the units for this one are amperes per volt, or else we can also define it as mhos. Okay. So this is output admittance. Now coming to the forward current gain, which is defined as HF. HF is defined as a short circuit forward current gain. Short circuit current, forward current gain. Forward current gain means output current by input current by short circuiting the output voltage or else output port. So V2 is equals to 0 and the units for this one are, these are unitless or else dimensionless. So this is HF. Okay. Now define a two-port network. So what is a two-port network? A two-port network of an equivalent circuit is defined as a circuit having input port and output port. So as we all know that transistor can be approximated as a two-port network where we have three terminals, right? Emitter, base, collector. Any one of these three terminals is taken as common between the input and output, and among the other two terminals, one is taken as the input and the other one is taken as the output, and hence we can approximate the transistor as a two-port network. So this is port 1, or else we can also call it as input port, and this is port 2, and the current flowing is I1 and the voltage drop across this one is V1. Whereas the current flowing is I2 and the voltage drop across this one is V2. So that means a two-port network of an equivalent circuit is defined as a circuit having both input port and output port, whereas a transistor can be approximated as a two-port network by taking one terminal as common between the input and output port, and among the two terminals, one is taken as the input terminal and the other one is taken as the output terminal. So these are all the definitions related to the bipolar junction transistor, that is related to the module 2. I hope it is clear to you all. That is all for this lecture. So in this we have seen the basic definitions and terminology used in module 2, that is bipolar junction transistor. I hope it is clear, and that's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.